Let us consider example 3, where we want to determine our node voltages at nodes A and B using node voltage analysis. We will proceed with our standard 4-step solution methodology. Step 1 is to assign our nodes A, B, C, and D, as seen to the left, where D is designated as ground, as well as the leg currents, where I1 runs through our 80 ohm resistor between nodes C and A, I2 runs through a 75 ohm resistor between nodes C and B, I3 runs through a 65 ohm resistor between nodes B and A, and I4 runs through a 50 ohm resistor between nodes A and D. It is noted that node C exists at the positive terminal of our 60 volt source, where node D exists at the negative terminal of our 60 volt source. Step 2 is to assign our voltage potentials consistent with our passive sign convention, where V2 corresponds to our 75 ohm resistor dictated by the directionality of I2. V3 corresponds to our 65 ohm resistor, where its directionality is dictated by the direction of I3. V1 corresponds to our 80 ohm resistor, where its directionality is dictated by I1. And V4 corresponds to our 50 ohm resistor, where its polarity is dictated by the directionality of I4. Step 3 is to determine the number of KCL equations necessary. We have 4 nodes, less unity, less our number of voltage sources, which is 1. Thus, we need 2 KCL equations. Typically, we'd apply a KCL equation at our supernode, but since node D is ground, node C is going to be equal to 60 volts. Thus, we will select nodes A and B to construct our KCL analyses. Applying KCL at node A, we first have I1 plus I3 entering is equal to I4 exiting. Applying KCL at node B, we have I2 and 100 milliamps entering and I3 exiting. Step 4 is to apply Ohm's law in terms of our node voltages. Starting with node A, we have I1, which can be expressed as VC less VA over 80 ohms, where VC is equal to 60 volts, plus I3, which can be expressed as VB minus VA per 65 ohms, is equal to I4, which can be expressed as VA minus VD per 50 ohms, where VD is equal to 0 volts. We now have to express our KCL equation at node B in terms of our node voltages, such that I2 can be represented as VC minus VB over 75 ohms, where VC is equal to 60 volts, plus 0.1 amps is equal to I3 exiting, which can be expressed as VB minus VA per 65 ohms. Now we have 2 KCL equations, and we want to re-express these in terms of VA and VB. Neglecting units and starting at node A, we have the following. VA times the quantity of 1 over 50 plus 1 over 80 plus 1 over 65 less VB times the quantity 1 over 65 is equal to 60 over 80. And at node B, we have minus VA times the quantity 1 per 65 plus VB times the quantity of 1 per 65 plus 1 per 75 is equal to 0.1 plus 60 per 75. Now, if we put this in matrix form, we have the following. 0.0479 VA minus 0.0154 VB is equal to 0.75. This represents our first KCL equation at node A. Then we would have minus 0.0154 VA plus 0.0287 VB is equal to 0.9. This is our second KCL equation at node B. Thus, solving for VA and VB, we have VA is equal to 31.8011 volts and VB is equal to 47.9899 volts.